Hello and welcome back to Calculus 2, section 8.2 on integration by parts. Yes. So what is integration by parts? Well, clearly integration technique. So we will be integrating functions using this section. And this one is going to be backwards product rule. So in Calc 1, when we dealt with derivatives, we learned product rule. And some of you did the product rule as a formula using f and g, and some of you did using u and v. So I'm going to use both notations to make everyone happy, because your happiness is our primary concern here. So the derivative of f of x times g of x is going to be f of x g prime of x plus g of x times f prime of x. Now, some of you learned this formula as uv, the derivative, is uv prime plus vu prime. Whatever. I don't care which one you use. Now, clearly, for the compact version over here, u is actually u of x, which is f of x, and v is v of x. It's a function. It's not a variable, just v as a number. It's a function. V of x, which is g of x if you compare it to the other one up there. So they are exactly the same, just using different notation. Now, clearly, this one is much faster to write. And what I'm going to do now is I'm going to derive the, what are we doing? Integration by parts formula, starting from the product rule formula from here. Now I'm going to take this formula here and use the Leibniz notation. So the derivative of u times v is going to be u times the derivative of v plus v times the derivative of u. Right? So this is what we are dealing with. Bueno? So let's see what happens when I integrate both sides. So when I integrate, I'm going to put integral dx everywhere. Like that. And we see that on the left-hand side, everything cancels, leaving us only with u times v. Now, on the right-hand side, these do not cancel. So we are going to keep this as, well, the derivative of, well, let me write it this way. You can't cancel until you write it dv dx plus integral of v du dx dx. Okay, now you can see what cancels. So integrals don't cancel. Only dx's cancel. On the right-hand side, everything canceled because it was the integral of the derivative. So they cancel completely. But on the right-hand side, only dx's cancel, and you still have dv's and du's floating about. So now you have u times v is equal to integral u dv plus the integral of v du. And from here, we solve for integral of u dv, which is going to be uv minus integral of v du, and that is the formula for integration by parts. Now, this is vanilla calculus, right? Not the honors section, so you do not have to memorize the proof, the derivation for this. However, if you do memorize it, it's a cool thing, right? Someone says, what's new? You can show this proof, for instance, right? It's awesome. Now, I do have one more way to show that this works, and that's the graphical way, because we can do the area under the curve and then just do some addition and subtraction there. So to show this formula in another way, I'm going to draw the function like, let's say like that. So this is my u-axis, this is my v-axis, and I'm going to color code these. I'm going to draw the blue shade on the bottom and point to this as the integral of function v du, because you see that u is on the x-axis, right? And if I draw a representative rectangle going up like this, it's a du rectangle. The top portion over here, I'm going to shade orange. And that one would be, as you can see, the sideways representative rectangle, which is a dv representative rectangle. So this one is integral of u dv. And now, if you are to add these two, you will get the uv, because, right, you can see that by adding orange and blue, you get the rectangle, which is u times v, right? So you can rearrange that. So now over here, this formula becomes integral of u dv plus integral of v du equals uv. And then from there, you go back into the formula. So this is a graphical way to prove the same formula, which is what you got earlier by fixing the product rule going this way. So that's what we have, right? The integration by parts is the backwards product rule, and it is very useful technique for later mathematics. If you ever took any graduate courses or something like that, more advanced math, usually in the hallways of those schools says, if in doubt, integrate by parts. A lot of proofs later on in mathematics actually use this, and then there are some linear operators and stuff when you do these things nested. You do 4 integration by parts inside. So for some advanced differential equation stuff. And so you're not going to see any of that stuff, obviously, here. And not even in undergraduate, you're not going to see any of that stuff. It's mainly graduate work where you would use it. Now, we use this to solve certain integrals, right? So this is a new integration technique, and it will be used to solve a particular type of the problem that cannot be solved in any other way. So the first example that we are going to work on is integral of x times sine x dx. So this is our first example to consider. And as it goes, right, in life, we would like to see if there is any old method that we learned at some point in life that we can use. So is this basic integral? No, right? Because it has 2 separate functions multiplied. It's not basic. Can we separate this into two basic integrals? No, because you cannot separate on the multiplication and division. You can only separate on addition and subtraction, right? If you have x plus sine x, you can separate into two separate integrals. The times cannot be separated, just like in derivatives you can't separate. You have a product rule for derivatives. Now multiplication in integration is dealt with either u sub or integration by parts. So we cannot separate. Now you ask yourself, okay, it's not basic, what's the next on my list? It's always, the next thing on your list is always u sub. Can you do u sub? Well, I need function derivative pair to do u sub. So I see two functions. There is, well, I see three functions, but these two are the same. So x and x is the same function x. So the derivative of x is 1. Well, that's present, but then I have an extra x there. So plus making u equal x, well, just swaps the variable, right? You are replacing x's with u's. You're going to get the same problem back, which is going to say integral of u sine u du. So you achieve nothing other than changing the variable. So you cannot go and say u equals x. That never achieves anything. And then you can say, okay, how about sine? Well, if you put sine next to bu, you do not have cosine for du. So u substitution goes out of the window. Not basic, not u sub. Therefore, this is the only technique one will learn, so it has to be integration by parts. Now, to do integration by parts, you set up a chart of these values. Let me write the formula one more time. When you rearrange it, you get integral of u dv is equal to uv minus integral of v du. So, what are the players in this game? U, V, du, dv. Those four, right? You have 6 things over here. U and V repeat twice each. So we have the 4 players. Now, look at this, guys. You go like this. U equals, dv equals, and then du equals, and then v equals. So that will be the setup. There are other ways to do it, but this is one of the cool ways. So your job is to break these into there. Clearly dx will always be what dv is. So your job is to transfer these in there. And clearly there are many ways and many combinations that you can use, and most of those will be wrong, right? There is one way to do this correctly. Now you're going to ask me, so how do I know out of 10 possible, well, experience and homework problem and doing 1,000 problems. That's how you know it. That's the way to learn it. There is no, magic way of doing this, and trust me, essential oils won't help. So they never do. So I'm going to start this by placing an x here, and then sine x dx in here. So why am I placing an x with u? Well, see, the u part gets differentiated, and that's going to kill the x. You see how x is actually what messes things here? If this x wasn't here, it would just be a basic integral of sine, and I'll be like, woohoo, done, right? But the x is there, and it's bothering me, right? So what do you do when something is bothering you, right? Get rid of it, right? So, right. So we put u to be x, and now when I differentiate that x, gone. You just have dx, right? Derivative of x is 1. This is like doing that u substitution part, right? When you when you have u and then you have a du. So you differentiate x becomes 1 dx. Done deal. Now over here, you have your dv. Now you need v. So how do you get v out of dv? You integrate both parts, right? So when you integrate dv, you integrate 1 dv, you get v. And when you integrate sine x, what do you get? Negative cosine x. We do not have to put plus c for this integration because there will be a plus c at the end of the problem when we are done with everything. So don't worry about plus c. This is a side calculation that you have to do. And believe it or not, you're done, right? Because all you need to do now, you have these 4 pieces, you just need to stuff them in here. Now, the reason why I like to organize in this way is because I can put my sheet arrow like that. Do you see the way the arrow goes? U times V. See how it goes, connects U and V? U times V and then V du. Do we all see that? Look at the formula. The formula that you need to compile, you need to plug this U is x, so that goes there. Your V is negative cosine, that goes there, minus the integral V is cosine, and then whatever du is, in this case dx, goes there. So U times V minus V du. The arrow helps you with the formula. So what is the solution now? Well, it's x times the negative cosine x minus the integral of negative cosine x dx. Here is your u, here is your v, here is your minus, here is your integral, here is your v, and here's your du. You compare this to the formula. uv minus integral of v du. So arrow helps us figure out the formula. Now do some algebra, integrate cosine, and we're done. So negative x cosine x plus the integral of cosine x dx is equal to negative x cosine x plus, what's the integral of cosine? X plus
C.
We're done. Oh. Have you heard of the layers of hell? Number 1.
Oh, yeah.
It's gonna.
X the hell.
Yes.
I'll just start crying now.
We progress. It's like, it's not bad. Of course, not bad. I invested time to explain this. My heart and my soul, right? The care, right? So over here, what you see is what we would call an introductory example to integration by parts, because we had to do integration by parts only once. It was clear that we need to get rid of this x somehow so that we can deal with the rest. You can see that the second integral over here lost that x. Integration by parts help us remove that x. And now we were able to integrate easily, right? So that's the purpose of integration by parts, to try and deal with the product in a way where you are removing that pesky x in front to solve the problem. So now we can add a little bit of heat gradually, right? So we are going from a regular temperature to, let's say, 150 degrees. So say you have Xe to the 3x dx. Right, so this is the next problem. And we immediately see that we can't use basic u sub, because if you set u to be 3x, then your du is 3, but you have x. So u substitution doesn't work. So we are going to set up immediately for our integration by parts. So u dv go on the top line. Below, we match it with the du and the v. See the movies? So now we're going to go with same kind of thinking. I need to really get rid of this x, because the rest should work fine. How do I get rid of the x? Well, put it for u, and when I differentiate, I'll just get dx on the bottom, and it's gone. So, yay. Nice. Now, if I took this one out and used it for u, then the rest of the problem has to be dv. So, e to the 3x dx. Now, I need to integrate that piece. When I integrate that piece, I will get e to the 3x divided by 3 as the integral. So that's a separate integration, right? You might have to use u sub for that integration, right? Depending on the spice level of the problem. Now over here you memorize that e to the ax is e to the ax over a, so you didn't really have to use integration, use substitution, but then, you never know. So now I'm going to put my arrow, which helps with the formula, and rewrite the problem as u times v, which is x times e to the 3x over 3, minus the integral of e to the 3x over 3 times dx, which is du. And I'm going to, one more time, say that this over here is u, this over here is v, minus the integral of this over here is v, and this over here is your du. Over here, I can call this u, and I can call this dv, and there's the integral. If you want to match the formula 100%, right, when you break it down into these pieces. So now what happens? Well, we have our 1/3 x e to the 3x minus 1/3 the integral of e to the 3x dx. So all I need to do is to integrate that piece. So I have 1/3 x e to the 3x minus 1/3 times e to the 3x over 3, right? And then plus c. So you have, you got another over 3, because you have to copy the one that it's already there, is the one that I kicked outside, which is the one that it's still here. And then when you integrated this, you created another over 3. So now, what we are going to do is we're going to factor as much as we can. So you can kick out 1/3 e to the 3x, and what's left in parentheses is x minus 1/3, and then you have plus c at the end. Now you're gonna go, do I have to simplify? And I go, if you are computer science, yes, you have to. Yes?
So you're trying to set up like the dv so that when you make the vd, the integral of v du, there's you can just use another integration method also.
Yes.
So that's what you're trying to say.
So first of, yeah. Now, you are going to run into a whole spiel of problems where various issues are going to arise. There is one rule that you should always keep in your mind. Don't put in dv something you can't integrate, okay? Don't put it there, right? Because you can't go here, and your problem is done. So if you make your choice for u, and then you put here something you can't integrate, well, clearly you have to make different choices, right? So that's one of the clues. Generally, we try to kill x. Generally, we try to do that, because this problem is a joke if x is not there. But that x is exactly what messing things up, so we have to use u sub. And by placing that x for u, it gets killed here by du, and then it doesn't show up when I have to integrate again, and awesome, right? Is that always going to be the case? No. Most of the time, yes. Always? Not always, right? Because it depends on what other functions you can stuff over there, right? And certain ones you can't integrate, so then it's an issue. Level 2 achieved. Let's crank the heat. Now, this problem is annoying because it seems that u sub can be used, but then as soon as you try, it's not pretty, and then tears and tissues and all that kind of stuff. So the first thing you are looking for is to use u sub because that's cheap, right? U sub can be solved, problems can be solved quickly, rather quickly. So you should be trained by now to look for function derivative pair, to look for sine with cosine, to look with tangents with secants, to look for e to dx with another e to dx, right? To look for root x and another root x in the denominator. Right, so function derivative pair is very important, and in that part, function derivative pair, you also find x squared and x, which is what you have here. So for a split second, it looks like you should be able to use u sub, but then, you realize it's backwards. We need the x within sine to be squared. Because if I put the x squared I have in this problem, if I put that x squared to be u, then the du part is going to give you 2x, and then that x is buried within sine and it's useless. So, can't do it. So if this square was on the other x, the problem would be u sub. But because the square is on the x in front, it's integration by parts. So now we are going to do integration by parts, and clearly, right, the x squared is the annoying part. So we're going to try and kill x squared by placing it for u, and then use dv for sine, because I can integrate that, it's all cool, right? So let's go. Integration by parts, it's u equals, we'll put x squared over here, put the dv sine x dx. Then we're going to go with the du to be 2x dx. And finally, v is good old negative cosine x. We don't have to worry about plus c. Put my trusty arrow over here. And let's go. uv. Well, that's going to be negative x squared cosine x. Minus the integral of 2x negative cosine x dx. I'm just going to clean this up. So there's a plus over here. I can even kick 2 outside and have x cosine x dx. What now? Yes. Very good. There were 2 cookies. on a test. You're supposed to eat both every time. Yes, you eat both. X to the ninth, not an issue. 9 integration by parts. It takes time, but 9 integration by parts, no issue. The square on that initial x tells you how many integration by parts you have. So it's not going to be an issue. You see x to the 9, 30 minutes of your life down the toilet, but you got it. You know how to do it, okay? So let's go. One more integration by parts. This one is going to be orange. We have u to be x dv to be cosine x dx. Du is going to be dx, and v is sine x. And we put our arrow. So now we have to be careful because there's going to be parentheses and multiple terms and multiply everything by 2 and all of that good stuff. So negative x squared cosine x plus 2 times open parenthesis, and this is where the orange stuff goes. So I'm going to put it orange. I have x sine x minus the integral of sine x dx, and then the parenthesis closes, and we see that the orange integration by parts now is nested within the old integration by parts. Now with the word nested, this is where all the computer science geek goes, yes, I know exactly what he means because I do nested loops in my programming class. So this is gonna be awesome. So for you guys, you know, I++ all the way to 9. Well, the special request, right? I mean, I don't want to be ignoring you. X to the 0. Then it's u sub, you're done. Or a basic. So we have negative x squared cosine x plus, now this 2 will distribute. I have 2x sine x minus 2 times, what's the integral of sine? Very good. And then we finally have plus c. Now there is nothing to factor out of all 3 terms. You do have pairs for factoring, so we're not going to bother to factor anything. Now this is the answer, right? Your integral is equal to this. Let's say you care, hypothetically, and you want to check. What do you do? What do you do? Ask me to do it. I just did it. Yes. You take the derivative of the red box and you are expecting to find x squared sine x as the answer of that derivative. Yeah, let's do it. Why not? So let's check. What color should I run? Green? Should I do lighter or darker green? Dark green. Match the soul. Good. Check. There is a rainbow one. Next. Yes. As you can see, right there. Second row from the bottom on the left. So I got you covered. We are going to differentiate the red box to look for the right result we need. So the derivative of negative x squared cosine x plus 2x sine x plus 2 cosine x plus c, which will go to 0 when you differentiate. All right, we got 2 product rules here, and then the basic derivative, and then the 0. So let's go. Copy the first, negative x squared, times the derivative of cosine is negative sine x, good, plus copy the second, which is cosine x, times the derivative of the first, which is negative 2x, good. Plus, now we're working on the next term. Also product rule. Copy the first, derivative of the second, plus copy the second times derivative of the first. And then plus the derivative of 2 cosine x. Derivative of cosine is negative sign, so this is going to be minus 2 sine x. And then there's plus 0 for c, whatever. So what do we have? Negative and negative give us positive. I have x squared sine x minus 2x cosine x plus 2x cosine x plus 2 sine x minus 2 sine x. Oh, look at them. They all lined up to cancel over here. And there is the x squared sine x. You can lead with this problem for the Thanksgiving dinner when they say what's new with you. You can lead with this one. Well, this is definitely not for you then. Okay, so I'm going to give you one to practice because it's not fair for me to have all the fun and you just stare at this, right? So integral x ln x dx. I'm gonna go get some water, walk around. You can take a look at this real quick. X ln x dx.
Oh, yeah, no, I. The ln throws me off.
You just want to see if all the brick walls are okay still?
Yes.
So how's it going?
It's not.
It's not, right?
What? It's not. Is there a check in here?
Of course, I'm a terrible person for asking you this. What's you? Really? Ah.
Oh yeah. Okay.
Because if u is x, then ln x goes for the integral. How are you going to integrate? What's the integral of ln x? You don't know that. That's not a basic integral. You can't integrate ln x. Yeah.
I'm getting you and DC.
So there is a problem where you don't get to put the polynomial on u. Oh, it's an exercise. It builds the character. So u equals ln x because, guys, you can differentiate anything. You have to focus on dv because you can integrate certain functions. That's it. You can't differentiate. You can integrate only certain functions. You can differentiate anything. So now, what's du? Very good. And what's v? Excellent. So now we put our arrow over here, and we write x squared over 2 ln x minus integral of x squared over 2 times 1 over x dx. So now you see that this x squared, right, and x, they cancel. And you have 1/2 x squared ln x minus the integral of, well, kick a 1/2 outside, of x dx. And as you can see, you can do it now, right? The 1/2 x squared ln x minus 1/4 x squared plus c. Now it makes sense to factor. So we have 1/2 x squared common factor, and then you have ln x minus 1/2 plus c. Ta-da! What was that? You don't believe me? Just go ahead, differentiate. Of course we're going to do another one. We're going to do a lot of these. We have to. So what was the issue to solve this problem? You can't, me being mean, yes. Deceiver, yes, yes. I have many names. There are thousands living within, right? What was the issue where you couldn't use x for u? What was the issue? The issue was couldn't integrate ln. Well, it wouldn't be the natural question for the next problem. What's integral of ln x? That's the derivative.
That's what I remember.
You do?
Because my calc one teaches trick.
person after my own taste, I would say. Great. Go ahead. Have fun.
Yeah, this has a U and a D in it.
Yes, it does.
It's only on like one. So it uses X. Let's just see.
So is it the basic integral?
No.
No. Is it a u sub? No. So by process of elimination, it is integration by parts. Great. So I immediately set up u dv, and then we have to think.
X ln x minus 1.
Nice. So what should we do?
ln x is for you.
So u is ln x, okay. And what's dv?
Dx.
Dx only. See, you are always going to have a minimum of dx in a dv. That has to be there minimum. You might have more stuff, like we had in all previous examples, we have more stuff than dx. But for dv, dx is guaranteed in there. You can't have it a blank. And we couldn't put ln there because you can't integrate ln. Well, that's what the problem is about, right? So now du is 1 over x dx. And what's the integral of dx? X. Now we put our trusty arrow over here. And we get x ln x as I multiply on a diagonal going down, minus the integral of x times 1 over x dx. Oh, this is cool. I just have to integrate dx, right, when x is canceled. So what we get is x ln x minus x plus c. And since we have computer science people present, we factor out x. Ln x minus 1 plus c. There it is. Now, do you want to memorize this as a formula, or do you want to crank this every time you need it? That's going to be determined on individual basis. I am going to write it as a formula because I can. But then, in the end, you decide what you're going to do with this.
What would you do?
You mean memorize it?
Yeah.
Well, you weigh it if you're going to use it. Let's say this is your last calculus class ever. Why? Right? You're done. I've been doing this 20 years, so I kind of have to.
So you kind of memorize this without even trying.
Now we're talking. I actually don't.
Right after
See?
class all the time. Nightmares.
Yes,
Homework.
I can help with nightmares.
More or less.
If you have issues, with nightmares, just don't sleep. It's a solution. But then they say, no, but I have to sleep. Well, if you hate clowns, it helps. Because you can just imagine every time you fall asleep, there's a clown right there next to you. With the balloon. Yeah, I'll do that. Okay. Enough games, right? Let's do some serious work. So, at some point in history, someone said, let's integrate this. It's going to be fun. Do we see the issue here immediately without even starting the problem?
Both of them are never-ending derivatives.
Exactly. Both of them are never-ending derivatives, so no matter which one you put for u, which one you leave for du, you can integrate, you can differentiate, you can never kill either of them. Right? Like Hydra, exactly. Wow, I'm gonna change the name of the problem. Hydra. Okay. So what now? Well, obviously it's in this section, so let's just do integration by parts and see where that takes us. So naturally u equals, let's go with e to the x, dv equals sine x dx, du is e to the x dx, and v is negative cosine x. And then we have our arrow. And I see the evil smile you have, so it matches the title. Good. You remember this. All right, so what do we have? Well, we have negative e to the x cosine x when I multiply uv. And then minus and minus will give me a plus. For the formula here, I'm going to have e to the x cosine x dx. And we didn't achieve much, right? But then, right, as you said, right, what's the definition of insanity?
Doing the same thing over and over again.
Expecting a different outcome, right?
Okay.
So that's why exactly we're going to do this one more time. Right? Yeah. There are institutions, but we can do it here. It's okay. U equals e to the x, dv equals cosine x dx, du equals e to the x dx, v equals sine x. And we put our little arrow here. We have to copy the first term, negative e to the x cosine x plus, because we are only working the by parts procedure for the integral, which means that we have to copy the first part, right? Anytime you are redoing this procedure, you just copy the front. Let's say you have 4 of these. Keep copying. So what do I have? Well, let's go and write in the orange stuff. And that's going to be e to the x sine x minus the integral of e to the x sine x dx. So we did this again, right? Expecting a different outcome, and we actually landed in the same problem after doing this twice, right? And life is now awesome. Please help us. What should we do, man?
Now you can just subtract negative e to the x cosine
Yes.
and the integral of e to the x sine, because they equal each other.
Yes.
So it's just
Now you're
One
going.
more time.
Now you're going to do something you have never done in calculus before. So, what's his name? Gregory. So what Gregory said is, you see that the original problem and this one over here are exactly the same. So how about you move this one to the other side and add them together? Like apple plus apple is 2 apples. Yeah. So, do you all agree that the top integral, your problem, is equal to this whole line? Well, redo the problem and you will agree. Because we did 2 integration by parts to get there. So now, original problem is equal to this. And they ended up having the same integral in it. So now you're going to take this integral, move it to the left side of the equation, and just add the 2 integrals, which creates 2 integral of e to the x sine x dx is equal to negative e to the x cosine x plus e to the x sine x. It's like $1 million trick. Divide both sides by 2, and problem solved. So integral of e to the x sine x dx is equal to negative 1/2 times e to the x cosine x plus, no, minus, because when I factor out minus, yeah, it will be minus e to the x sine x plus c, and we move on with our life. So you are going to go and rewatch this as many times as you need, right? So let me just put in some basic math language what technically happened here. So I'm going to call the main integral m, and that was equal to some g. Let's go with the negative g. Negative g plus r minus another m. So technically this is what you had. Something like that. And then to solve for m, you move them to the other side and got 2m is equal to negative g plus r. And then you said m equals negative 1/2 g minus r. So technically that's what happened. Now I understand that all of these expressions were functions and integrals, but technically if you want to write the same problem in algebra and have the, all of these expressions be represented by letters or variables, the mathematics behind it is the same. You learn the form, not the example. So technically, what we had here is you have that m and you have that m. And then when you move the one from the right side of the equation to the left side of the equation, that minus becomes a plus. And then when they add together, they create 2 integrals. And then we divide it by 2 on both sides and solve the problem. Cool, right? Of course, math. So let's pick an example from the textbook to solve and call it a day. Because, that's what this is. That's not. You have the book. Awesome. So let's find something. I can see something spicier or.
I've been waiting.
This is our edition or this?
Yeah, this
Third? Okay. Just wanted to check so I can actually name the problem.
A little fast.
All right, so since exam is approaching, let's do a review problem and pepper in some integration by parts. So the problem 44 in 8.2 says, find the volume of the object which is generated by revolving f of x equals sine x about 0 to pi around x-axis. This is your exam question minus not these functions, right? Because this is coming up. So now we are going to, well, not this particular problem for the exam because it's using obviously integration by parts. But the formula that you have to set up for this is definitely on the exam. We are doing rotation on x-axis. So we're doing rotation on x-axis. And we have 0 to pi, which is why I only have a bump. It doesn't go under the axis, because under the axis would be the negative bump from pi to 2 pi. And I'm rotating on x. So what is my method of choice? Disk or shell? Disk, because I can do dx. Can I do dy? No, because dy folds on the same function, right? Both ends touch the same function if I do dy. Make sense? Of course, math. So we do dx. So since I have the x rotation and I must do dx, that means that I'm using disk. It's a single function, so I'm not using washer, I'm using disk. Okay, bueno. Let's go. What do I have to set this up? I have, first we have v equals, we have a single pi in front, right? Shell has 2 pi. Disk has single pi. Then you want the limits. Okay, here, make you happy, 0 to pi. Then we square the function, sine squared x, and then dx. Wait, why is this? Really? That's problem 44. What? This is definitely a review for the problem. I could have placed this on the test. Now I ruined the perfect problem. I guess next.
You can just flash this like when you black out.
Oh, blink. This is a joke. Why is this a joke? Because you have the power reducing formula. There's no integration by parts. There is no u sub. This is basic integral. You use the formula to reduce this to what? Very good. From 0 to pi, and from here, you just compute. So this is not something special. So when you plug in pi, we get pi squared over 2, right? Well, that was disappointing. Yeah, we're gonna try again. See if we can find something nicer. Well, the rest of these we solved actually in class. So let's find. We solved that one. Solved that one. We solved that one. Ooh. Number 21. Integral x sine x cosine x dx. There we go.
Well, I thought we were doing 44.
44 is done.
You did.
Now you divide 44 by 2 and subtract. Yes. 1.
We all
Different definition of fun? Yeah.
have. Yeah, like I like to do journal that relax my brain. Not really. What am I doing? Am I like
Math.
Yeah,
You're doing integration by parts.
of course.
No, it's different. That'd be like if there's a 2, like it was like
So this one could do
yes, this would
Exactly.
So it's like the UDV, but like DV is like side X
Still going, but it is we're here. We're here.
the X is
But our worries.
Exactly.
What makes bigger?
gets swollen.
Give them
And
brain games.
nothing very well. Because that was no, because it was no, that's yeah, why?
Oh, okay.
Because he factored out. No, well, that's what. What's
Well, I guess the sun is
All right, what do you got?
It doesn't go to 0. Like you know, like lower bound integral, they're like, oh, it's 0, so you not even do, you just do the upper one. No, with trades.
show me the way.
Yes. Yeah, we're best.
We need U, we need DV.
Is DV sin x cosine x? So I want it to be.
So what should we do? Well, if the x wasn't there, the problem would be easy, right?
See.
What would this problem be if x wasn't there? U sub, exactly. And if I remove either sine or cosine, the problem would be by parts because we opened with a problem that was x times sine. Okay, so then let's just kill x. because we can integrate sine x cosine x dx using u sub. Du is just dx, and this one over here we need to u sub, right? So to do the u sub, well, u is already used up, so maybe we do the g sub or something. Say g equals sine x, then the dg is cosine x dx, and you have integral of u du, and g dg, which is 1/2 g squared plus c, which is 1/2 sine squared x. Well, we don't need the plus c because we are. Go. Are we okay on this? Not really?
Is that particle?
You have two functions, and we are using u sub because we have a function derivative pair. So we are using u sub to differentiate. To integrate. We're using basic u sub to integrate here. So when we integrated, we came up with this answer on the bottom.
So b is equal to sine
Yes.
x over 2.
Yep. So now when I put my trusty arrow over here, I have 1/2 x sine squared x minus the integral of kick 1/2 outside, and we have sine squared x dx. Now that has to be dealt with a power reducing formula. So it's going to be minus 1/4 integral of 1 minus cosine 2x dx. And finally 1/2 x sine squared x minus 1/4 x plus 1/4 integral of cosine is sine 2x over 2 plus c. And there is nothing we can pull. We can pull out 1/2 everywhere, but we're still going to have halves and quarters left behind, so just leave it. 1/2 x sine squared x minus 1/4 x plus 1/8 sine 2x plus c.
Why is it? Oh,
What an awesome problem.
how does it become 1.1?
The formula for power reducing is over 2. So 1/2 times a half from the formula. The sine squared power reducing formula has two in denominator. Wait. Yeah. No, it's cosine. For both of them, it's cosine.
That's one of those things I should have memorized already.
All right. That's it. Now go home, do homework.